So today we finally are, and we're going to 12.8. So, we're going to start this not dealing with imaginary anything. We're just going to start this with algebraic values that you're familiar with. We've got A, B, and then we'll throw in C and D in a second. So we start out with some value A, and when I square A, I get B. When I take A times B, it's really like doing A times A squared, since B is A squared. So then A times B, we're going to go ahead and say that's C. So if you take A times B, you get C. So A to the fourth then, we'll just call D, because we can make it B times B, or, because think, if B is A squared, then I could do B times B, which is really A squared times A squared. So really it's A to the fourth, but we're going to call that D. And then we could say A to the fifth has a variety of options for what we could represent it with. We could say A to the fifth is B times A. We could say A to the fifth is D times A. We could say A to the fifth is just A times A times A times A times A. There's a lot of ways we can represent this.
It's kind of like the question we did in math counts that asked us how many ways can you make 67 cents with only pennies, nickels.
Yep, exactly. So these are kind of like, not exactly like placeholder values, but it's kind of just representing, okay, A is our smallest unit, we square it, we get B. We then multiply by A again, we get C, and we move on from there. So we could fill out a whole table relating to this, but why that really matters is when we say A squared is equal to B, that's the basis of where the imaginary number comes from. When we say that something squared equals -1, that means that that something, when I square root it, gives me the radical of a negative number, which we know two numbers cannot multiply by each other to get a negative value, because a positive times a positive gives me a positive. A negative times a negative gives me a positive. So this is where we really come up with that name of the imaginary number. We can work with it. We can represent it. We can talk about it. It's like when you were a kid and you had an imaginary friend. You could feed it peas. Might not work very well, but you...
I never had an imaginary friend.
I'm sorry you missed out.
Neither did I.
Real ones.
So, although people less advanced in math may not understand it, they might say, no, there's no such thing as imaginary numbers. We have numbers and we have not numbers, and that's it. We know that that's a lie. We have the imaginary number I. So we introduce I. It's very small up on here. I don't know exactly why. So on your notes, I is your imaginary number. It represents radical -1. But when we go to use I, we essentially factor out the negative amount of the number. So if we start out with a negative A, doesn't matter what A is, I can pull out the negative by saying really it's -1 times A, because that's how you make any number negative, is just multiply by a -1. Then I break up that radical, so I see it's really the radical of -1 times the radical of A. And then I can reevaluate this by just changing my radical of -1 into an I. I leave the positive radical under the radical, or if I'm able to solve it, I do it and I write it in either its integer notation or however else we can represent it. Working backwards, if I start with an I and I want to get rid of it, I can just multiply by another I, because as soon as it's squared, it turns into a -1. So if we work that process backwards again, you can see doing the essentially the inverse orders. You start with an I. Like, we know that there's going to be an I there. They went ahead and wrote the squared, but if we think about like -5 taking the square root of it, well, we can't because it's a negative number. So instead we say I can take the square root of 5 and pull out the I, and then I can evaluate the whole thing by squaring. I turns into -1. It's essentially like working it backwards to check our work. That makes sense, yeah, because I saw your slight confusion. And the other key concept here is when we talk about a complex number is a real number and an imaginary number. And because they're not like terms, we cannot go ahead and combine them, but we can express them together. So we essentially write it like a binomial. We have our constant value a and our imaginary value that's always going to have an I attached to it. It might just be I, it might have a coefficient. That's going to be our imaginary part.
Wait, why do we need imaginary numbers?
To represent the radical of any negative. So you'll get into math where you get like square roots of negatives and you want to keep going, but you can't unless we figure out a way to express that. So we invented, like mathematicians somewhere back the line, invented I to just be a placeholder. It's essentially saying you can't go any further unless you have this special key. And I is the special key.
Is it like a key card, like for the hotel doors?
Yeah, they reprogram it every time it gets. Yeah.
Oh, okay. Like, what's the fee for like losing one? Is it like $10?
They're pretty forgiving.
Okay. Is it 21?
So when we look at approximating radical negative 18, we want to re-express it. We want to use the imaginary unit I. The first thing I'm going to do, Leon?
3i radical 2.
Oh, first thing we do is break it apart. We do not jump right to the answer.
Boy.
So, is this solved on your paper?
Yes. Yeah.
Okay. So, I went ahead and gave you that solution so that it made sense. But we first start by breaking it up, pull the negative out from the 18. Then I evaluate them both separately. Radical of negative 1, radical of 18. Radical of negative 1 turns into I. Radical 18, I can break that up even more. So you might want to notate there it's actually radical 9 times 2 is how they did that. Since 9 is a perfect square, that's where the 3 comes from. And because radical 2 cannot be expressed nicely, we leave it in the radical. Getting blank faces. Questions? Comments? It's just like evaluating any other radical, except we pull out the negative first and we just turn it into an I.
Wow, just because I have the answer, Jacob.
Where does the I
Right
come
here.
from? Oh, I was like, it just like randomly appeared and then the other thing.
Because radical negative 1, I change into saying, oh, well, that's I, because it's imaginary. I can't do it, so I represent it with imaginary numbers.
Okay.
All right, try this one on your own. Start by pulling out the negative. Hopefully this isn't done on your notes.
Put your hands down.
Jacob, did you have your hands on? Let other people follow. This is what happens when you inflame a competition between both of us.
Oh, now that I know that, I was not calling either of you. Grant.
It's not like Jacob
Is it
doesn't do it.
2 I? No.
Well, I don't know. I can't just jump right to the answer.
Okay then.
I'm serious, dude. When I look at this, you guys are in this like, ooh, let's just get to the answer. Do the process. Take some time
Split
to
it,
enjoy the
yeah.
process.
Yeah.
So split
Get
it,
the negative out of there.
then.
Get the negative out of there.
So then I really take them both separately.
That's just imaginary.
This is just imaginary.
And you split the 12 into a 3 times 4.
A 3 and a 4.
Take the 4 out of there. So 2. So 2I radical 2.
Yep. 2I radical 3. We always use the lowercase I because, well, we just do. There's really no supporting detail for that.
Uppercase letters are for the lower class.
Are we okay with this? Evaluating negative radicals.
If I can do it, anybody can.
We break it up, get it to simplest form.
Whole paper in uppercase letters.
Now,
Probably do this.
we're going to take this lesson even further of a stretch. We're now going to graph these imaginary values.
Bruh.
So, to do this, we need an imaginary graph. If you're going to have an imaginary number and you're going to graph it, you're going to need an imaginary graph. So, we create a graph with a real axis and an imaginary axis. So, my real axis is what used to be the x-axis. My imaginary axis is what used to be the y-axis. And notice, it's labeled with I values. So each box changing vertically is a value of I, or each box is really representative of the radical -1. But we don't want to write that. That's really annoying. So we just write the i's. Mackenzie?
Is the imaginary axis always the y?
Yeah, we make the imaginary axis the vertical one just because. That's just how we like it. You can flip it, but that won't, like, we just do this normally. So, -5 plus 3i, you just graph over to the -5, up to the 3i.
How did you get to like the absolute value?
So, we want to look at absolute value because we're looking at the like positive of it. There's also the negative because when you deal with radicals, you get the plus or minus situation. So that's why we're really thinking about, okay, if we only look at the positive here, but remember it's imaginary.
And then why was square it? Why in the radical? Why was
So it's squared to show that the only reason I have that square root is I'm also squaring, so they're like canceling each other. The square root and the squaring are both there because I essentially didn't do anything, quote unquote.
Oh, but you got rid of the negative.
Yeah, I got rid of the I.
Oh, yeah.
Because, so from here to here, I squared both values and I took the square root so that I didn't do anything. Because if I squared and square rooted, it canceled out. That's like saying I multiplied by 3 and divided by 3. Well, okay, then you didn't do anything. So when I square the -5 squared, but then remember the square root will be out there. And when I square the 3i squared, well, my 3 is going to get squared, and my I turns into -1. But since I'm looking at the absolute value of it, we just... Because I'm squaring and square rooting. I'm essentially doing nothing, but I want to get rid of the I. And the only way to get rid of the I is to square root it, or square it.
Can't you just like pretend you did nothing and then just take away the I?
No, because then it won't be right.
But then you just
Because this
That's
becomes...
like the same thing.
No, this becomes 25 plus 9.
Oh, so you have to do that.
Yeah, you have to actually evaluate it. You can't just act like you did it. That's where we get the radical 34. So we could then say -5 plus 3i equals a radical 34. Not that that's, any nicer, but that's a new way that we can evaluate it, that we can look at it. Because it's imaginary. We can't work with it because it's imaginary.
But then why do we have it in the first place? Hey, at least my best friends are Muppets.
What?
Alright, let's look at just graphing 6i. We would only need the imaginary axis because it's 6i. I mean, we obviously are still going to have the real axis to be in 3D space. But what would I do to graph 6i? Carp?
I'm pretty sure you just go up 6 star.
You just go up 6. Now, when we evaluate the expression, I start with my 6i, and I only want to evaluate the absolute value, the positive. So, I square it, but I also have to square root it so that I don't actually do anything. So when I square this whole thing, and then square root, I'm going to get radical.
36.
Okay, yeah, but do you understand how we get there?
Yeah.
Okay.
I don't.
So the 6 is going to get squared. The I gets squared. When the I gets squared, well, I guess I can go ahead and write that out. That's 36. But the I gets squared is -1. But since we're only looking at the absolute value, we started with absolute value. I can't have -1. I really only have the positives. Sorry, this was multiplication, not addition. So it's really just times 1 and it's gone. The only reason we have this 0 here is they wanted to write it in complex number form, and there is no real number with it, so that 0, it doesn't need to be there at all. Grant?
So why do we square it if we're just going to square root it?
Because if all I did was square it,
Can't we just get rid of it? Just kill it?
if all I did was square it, I've done something. I've changed the expression. That's like saying if you start with x equals 6 and all you do is square it, then you end up with x equals 36. Because I can't square on both sides. I don't have two sides. I just have an expression. We don't have an equation, but just an expression. To keep the expression what you started with, you have to do it and undo it. That's why we square it and square root it. It's so that I have not actually done anything. All I did was change how I can look at it. I re-evaluate it. That's like saying 6 is 3 times 2. Or 6 is 5 plus 1. Or like, you can say it in different ways. It's still the same like representation. It all plays into how we deal with quadratics. When there's a negative value in a quadratic, what it does to us, what it has to make happen. Just this is one of those things where you kind of have to learn it first and it makes sense later. So if we were to graph this, and you can use that same, I think I gave you a graph for this one, did I?
No.
Nope.
No.
No, sir.
Yeah.
So, like, for the previous one we did negative 5 plus 3i. Why? So, if we can't square root it, do we not use the front? Do we not use the function? Because in that one, we
This one?
yeah, we didn't use the radical for tool. We used negative 5 and 3i. Like,
Yeah.
It's confusing me because for the 6i one, we
So we're doing two different things here. We're graphing it and we're solving for what is the absolute value of that expression. So if we looked at like an absolute value graph, what do absolute value graphs look like? Like if you have the absolute value of x, Ben?
They're always positive and always on the
Quadrant.
quadrant.
3.
Yeah, 3. I don't remember well.
So if we had y equals the absolute value of x, it'd go up like that and go up like that. Because if x was 1, y would be 1. If x was 2, y is 2. If x is negative 1, y is 1. If x is negative 2, y is still positive 2. So we're only looking at positive solutions essentially. We're only evaluating.
That's not what's confusing. It's because in this one we didn't use like radical 34 as for anything.
Yeah, we're just trying to evaluate it so we know what it would be in a different form.
Oh, okay.
Don't get too hung up about the graphing part of it is not really important. It's just understanding, okay, if I have this much real and this much imaginary. Why?
Quick question. Can you label the quadrants of the graph real quick? I forget that. Like,
What do you think this one is?
It goes counterclockwise.
Is that one?
Yes. It goes counterclockwise.
Where's 2?
To the left, to the left.
Everything else.
So it's like,
Okay, that one's 5.
4.
Never mind.
how are you supposed to remember which one's which?
The quadrants?
Do?
You start in the top right, like everything starts top right normally,
Like positive,
and you just have to
positive.
remember counterclockwise.
Okay, got you.
Because we're starting positive, positive. Then we go negative, positive, then negative, negative, and then positive, negative.
So you go from
It's the x, y values. Yeah. And it's because how when we translate on the graph, Leah, if I rotate 90 degrees, that's actually a counterclockwise rotation. All movement in the graph is assumed counterclockwise.
For the graph, does it matter which one is x and which is y?
We like the x-axis to be the real. So for here, this will be graphed on my x-axis, and then my y-axis, but it's really my imaginary. Hey guys, can we come back? Thank you. So if we were to graph this, we just quickly sketch out if this is my real, and this is my imaginary.
Do you have to write real and imaginary?
Yeah, I mean you should.
Okay.
Because they're not x, y now. It's a graph of real numbers and a graph of imaginary. We would come over 1, 2, 3, 4, 5, and we'd come down to a negative I. And my graph would leave my point right there. But now the part that I think we're getting hung up on. 5 minus I. I want to evaluate the absolute value of this, so only looking at positive values. But I can't actually do anything. If I do something, it changes what we started with. So I'm going to square roots and square. Okay, not square the whole binomial. I should not have written it like that. So I'm going to square my 5, square my I, and then radical to undo what I've done. This will become 25 minus I squared is really negative 1. Sorry, these are multiplying. No, they are adding, yeah.
25 or 26?
26.
Cool.
I only doubted it because somebody said, wait, stop. This. So the 3 of you gentlemen cannot sit near each other anymore. We clear? Because we're looking at the absolute value, we treat everything positive. We make it addition. Jacob?
Are we really just using Pythagorean theorem?
How so?
Because you're finding kind of the length of that line. That's also because you're squaring
Yeah.
that 5 and then
The distance from the origin.
Yeah.
Yeah, so what Jacob's really looking at, this is further than we really need to go. This distance from the origin point where there's no real numbers and no imaginary numbers, this value of 5 minus I is radical 26 away. Right, that's what you're trying to say. It's like a hypotenuse. Because if we travel 5 to the right and then I down, what's the total distance that it went? That might, I don't know, that might help some of you guys, it might confuse some of you.
Can we just use Pythagorean theorem for those things?
What do you mean, can you just use Pythagorean theorem?
Because Jacob, you said if that for both methods, can we just use like Pythagorean and just solve for the absolute value?
Yeah, I mean, I'd want to see a few examples before I really stamp of approval, but it should work as long as you're thinking about it the same way that I am. Yeah.
Why would you want to solve it to the very end?
Why do we want to get to radical 26? Because that's our distance. That's really how far away it is from the origin. But here our origin is no value, no complex, no imaginary, no real, no value. So it is radical 26 away. We need to get to the point where we are applying this to a situation. This is why it's a lot of just dump it down the throat first. All right. Add. Huh? Yeah. When we add or subtract, all you're doing is like terms. So I believe this one's also done out on your paper.
No, it's not.
No? Well, here's the solution then. You have a 4 and a negative 4. Those are additive inverses. You have a negative 3i and a positive 3i, also additive inverses. So here the sum is actually nothing. That's not how it's always going to work. They just gave you a really easy one to start. So if we look at B, pay attention that that negative has to go through the whole second.
Can you go back?
Can you not see that? You might need to sit closer, man. They're additive inverses. So if I highlight to kind of color code this, those are reals, these are imaginaries, and they combine together both sets to make 0. So our like terms now, instead of really looking at same variable, same exponent, we're really looking for, is it real or is it imaginary? If it's real, then I have to ask, does it have the same variable everything else? So here, I start by distributing out that negative. So I rewrite this 5 minus 3i plus 2 minus 4i. I combine my reals, which gets me 7. I combine my imaginaries. Negative 7i. Don't forget your I.
Why are you bringing it back up to imaginary?
So try this one.
7's tiny.
Oh, is that all we have to solve out for?
Nope.
Oh.
This lesson is supposed to be easier than what we've done, but you guys are analyzing kind of deep and trying to get right to the what it does. We kind of just have to understand how to work with it first.
4i plus, minus I. It's 4 minus I, sorry.
Are you sure now?
Wait. Yeah.
I don't really need the 1 there, but just to emphasize, negative 2i plus an I brings me back to negative 1i. 7 minus the 3 takes me to 4. Questions on combining? You really like doing like terms.
Mr. Hudson,
Yeah?
because it's imaginary, is that why you use an I instead of an as a variable?
Yeah, that's why we never use I really as a variable. We try to avoid it because it, like some other Greek symbols, it is like specific to I means the imaginary number. So it's not a variable, it's representative of a value.
What about a capital?
Okay.
We
That's
should
what
also
we don't.
get rid of a then, lowercase alpha.
Yeah, so what's alpha worth?
A number.
There's all kinds of mathematical constants. So there's like Avogadro's constant, which
That sounds like avocados.
it does.
It's avocado
Constant.
What
are you
maybe? Without taking too long. This is not gonna give me. Maybe. No, this is kind of too deep into it. I'll find some other examples and we'll talk about that at some point. So now when I do multiplication, now this is when things start to get nicer, because every time I have two i's that multiply by each other, I can really re-represent that with a negative 1. So when I do this multiplication, I forget if it's done out on your paper or not, but I'm going to show you guys the solution anyways. My 3i multiplies by my negative 5, gets me negative 15i. My 3i multiplies by my 2i and gets me 6i squared. So you multiply your coefficients and you multiply your i's. Then my I squared, I replace it with negative 1. So that really makes my 6 negative 6. So I've got a real value and an imaginary value. Negative 6 minus 15i. Then?
I'm skipping ahead a little, but in the got it, not in the got it, but in B and C, couldn't we just use like FOIL?
Yeah, that's what it's supposed to be.
The photograph is hard.
So because I cannot combine my binomials, I cannot combine 4 with 3i, and I cannot combine negative 1 with negative 2i, I have to FOIL this. So when we FOIL this, 4 will multiply by my negative 1, giving me another real value. I'll get two imaginary values that can combine with each other, just like my b value that I get when I'm normally doing a binomial times a binomial. And then my two imaginaries will combine to make one real value that will be able to be combined at the end. I'm going to go ahead and list this out. you struggle at all, write out your work. What's your first, your outer, your inner? Your outer and your inner should always combine if my binomials are in the same form. And your last should make a real value. Yeah, Ben? You got the next one? No, capture. What do you think?
I did, so you get the first, which is negative 36, then you get outside, minus 6i.
Actually, positive 6i if we're doing the outside first. Then the inside.
And then minus 6i.
Mm-hmm.
And then minus I squared. And then you solve that out to get I squared plus 36.
So I'm going to bring down the 36. These combine. I'm going to replace this with my negative 1 because I squared replaces. So, Jacob?
You can always just use a squared, a plus b times a minus b equals a squared minus b.
Yeah, I mean.
And then, so what you get would be 37.
What we really have here is a difference of squares. If you didn't notice that. It's not in the form you're used to, but if you saw 2x plus 4 and 2x minus 4, the plus 4 and the minus 4 should indicate that they're going to cancel out. You have no middle term there. And since my last term becomes real, I combine it all down to one real number. Mackenzie?
Wait, so do you not take the square of the...
No, because the value of I squared is what makes negative 1. Other questions? I by itself, we can't do anything with. We have to square it to change how we evaluate. Try the Goddard if you haven't done it yet. 7i times 3i. Close. 21i squared. The I squared is multiplied by it. So I replace it with negative 1. It's negative 21. Those are multiplying.
Multiplication.
It's a negative.
You guys could make a new meme. Or not meme, but Vine or whatever. What's 7i times 3i? Negative 21. Huh.
That was just almost as bad as you driving by me and telling me, asking me what this
Yeah.
was 36.
You guys might be able to become famous though.
I was trying,
No, actually, it's negative.
man, this is square root of 36.
In this problem, you will divide complex numbers. Part A.
All right.
What is the quotient of the quantity 9 plus 12 times I divided by 3 times I?
We can only change I if it's I squared. Did I leave this solved out on your paper?
Yeah.
Okay, I kind of thought so. So, my first one here, what I want to do, and I, if I was you, would highlight or underline or something or write in, we multiply by 1. But my 1 can be anything because as long as I do the same thing on top and bottom, I haven't actually done anything. So if I multiply by a negative 3i on top and I multiply by a negative 3i on bottom, I technically haven't changed anything. That distributes through, gets me the negative 27i minus 36i squared minus 9i squared. I replace any I squares that I can with negative 1s. Then I evaluate this and I break up my division. So this becomes 36 divided by 9 minus 27i divided by 9. Now here's where some people have that like bit of confusion. But you got to think about it like if this was a variable term. If you had 4x divided by 2, you can do that. So even though 27i is imaginary and 9 is real, I can evaluate that and take the 27 divided by the 9 and just get the 3i. Minus, of course. Questions there? All right, try it on your own for the next one.
You might want to fix this calculator.
What?
Why are all the ones that I touched today?
Yeah.
They see your face.
Because we wanted to be able to get rid of whatever we could, and so we're gonna for sure have an I no matter what. Because if the 9 divides by 3i, that's gonna give me an I. But we really do not want an I in the denominator. Like, we don't want fractional values with an imaginary denominator. So we really say I want to get rid of the 3i in the denominator. So that's why I multiply by the negative 3i. Now if I just multiplied by the 3i, this would do the same thing, but each value would be the opposite. It would be negative 12 plus. Exactly. Yeah, we're trying to make it turn into I squared.
At least they can see what's coming.
So now this is a bit more difficult. The complex conjugate of this denominator, well before it's just the opposite. We'd use the negative 3i because we want it to become positive. We could have just used 3i, but it just would have been the opposite signs. But here, anyone know what we're going to multiply by?
Nope.
1 plus 4i. So you always want to take the opposite, like positive or negative, of the coefficient to the I. And we do that so that it turns positive. Because if I have a negative times a positive, then when the I gets squared, it's a negative, and the negatives cancel out. Now it is a difference of squares, and we do that on purpose. You cool with this? Because you're just staring at me and it's kind of creeping me out.
No,
Grant,
Yeah. What?
are you good with this? Does it make sense?
Like 4%, yes.
So I was over chatting with Emily about why we did this, why we multiplied by the value on both sides. We do not want an I in the denominator. We do not want an I in the denominator. If we have an I anywhere, it can be in the numerator, it's okay. We don't love it, but it can. To be able to express that imaginary value, it has to be in the numerator at least. So we've done this to get rid of the I in the denominator. That's why we're multiplying by its complex conjugate. Yeah.
I guess you could say you have to keep an eye on it.
Oh. Wait. I should have.
That's really creepy.
Sounds like the beginning of a Feel Good Inc. That song can, yeah.
Probably watching your
In this problem,
Can
I.
You just might need to sit closer. That's why we got the TV. Because we have like 2 minutes left and I'm trying to cover one last thing. Try the Goddard on your own. That complex conjugate. I'm going to jump over there. Remember, you're going to use the same constant value, but the opposite of the imaginary value. So that complex conjugate should be 3 minus 4i. Great. Can I move on, dude? Sweet. Thanks. So we're going to multiply top and bottom by 3 minus 4i. I can go ahead and identify that because the difference of squares, the outer and the inner, will cancel each other out. So really my denominator is just going to have the firsts, my 3 times my 3, which is 9, and my lasts, which turns into minus 16i squared. Now my numerator, are we cool with the denominator? I care more about the denominator than I do about the numerator, because that's why we chose to do what we're doing. Then this is going to become 9 minus 16 times negative 1, which is really going to become 9 plus 16, which is really going to make my denominator 25. Now I got to look at the numerator. My first gives me 15. My outer gives me negative 20i. My inner gives me negative 6i. And my last gives me positive 8i squared. Now my I squared, we know, is really negative 1. I can combine my two other I values, so I get 15 minus 26i minus 8. I can do the 15 minus the 8. I get 7 minus 26i. So then I can split it to have a real and an imaginary. I get 7 25ths minus 26 25ths I. So please come to class with questions so that we know what we need to go over some more. Try this homework out. Let me know what gives you issues. We will go at whatever pace we need to get this stuff figured out. Everyone get one? Well, it's a complex number because it involves an imaginary. So, the imaginary is any number that involves the I. Complex is any number that involves an I and another value that is the I. So, like what we ended with here, this is real, this is imaginary, which makes the whole thing a complex binomial. Alright, so what are the specifics that we need to discuss?